Hey everyone, welcome to day 7 of our derivatives and integrals challenge. Today we're going to do an implicit differentiation with this guy, and then we're going to do some integration by parts. So let's get to it. For the first one, we're going to again use implicit differentiation. So we're going to differentiate both sides with respect to x, right? Take d dx of both sides. So on the left-hand side, we are going to have cos of xy times the derivative of the stuff inside of those brackets. And so that means cos of xy times, and then we're going to use the product rule on the xy. Okay, so the product rule means the derivative of x times y, that's just 1 times y, plus, and then x times the derivative of y. Now, again, we're taking the derivative of y with respect to x, and so that's where we get our dy dx factor. And that's the left-hand side differentiated, okay? Now, the right-hand side is, again, going to need some implicit differentiating. So, product rule, we're going to do derivative of x squared times y, so that's 2x times y, plus x squared times the derivative of y. That'll mean x squared times the derivative of y with respect to x is, again, same as here, dy dx. And then again, for this last term down below, we're going to need the derivative of x times y squared, so that's 1 times y squared, plus x times the derivative of y squared with respect to x. That means 2y times, again, that dy dx factor, okay? So we have quite a bit to clean up. On the left-hand side, we have the cos of xy times y plus x dy dx. And on the right-hand side, we have 2xy plus y squared plus x squared dy dx plus 2xy dy dx. And now the whole point of this process is to get an expression for dy dx all on its own. And so what we would be wise to do is to get all the dy dx's multiplied through and then group them together on one side so we can factor them and isolate them, right? We're going to isolate dy dx the same way that we would isolate y back in junior high, okay? So let's multiply through the cos of xy times these brackets. So we'll have, let's see here, we'll have y cos xy plus, let's do x cos xy dy dx, okay? And then we'll have, okay, I'll just rewrite the right-hand side. Same way as before. Oopsies. Not what I wanted to do at all. There we go. Plus 2xy dy dx, right? Okay, and now my dy dx's are all multiplied through, so let's move them all on one side, and let's move every term without a dy dx on the other side. Okay, it doesn't matter which side. We typically have dy dx on the left as dy dx equals whatever. Let's keep going with that strategy. So let's move. We're going to move this over there, and we're going to move these. Nope, the other way around. We're going to move these two guys over here. So that means that we'll have, on the left-hand side, I'm going to factor out a dy dx from all three terms. Notice how dy dx is common to those three terms, right? That's why we wanted them all on the same side, so we can isolate that dy dx by factoring it out of all three terms. And so that means we get dy dx times x cos of xy minus x squared minus 2xy, right? Once those are all on the same side and dy dx is factored out, we get this minus that, okay? And on the right-hand side, we'll have 2x squared, 2xy plus y squared, and then this term subtracted on both sides, and so minus y cos of xy, like so. And then the last step is going to be isolating dy dx, right? Which is what we wanted to do all along. So to get our expression for dy dx, we're going to divide both sides by that whole thing. So that's x cos xy minus x squared minus 2xy. Same idea here. So x cos xy minus x squared minus 2xy. And now these guys cancel out, obviously, right? That was the whole point. And so let's see if I can make some room here. That means that we get an expression for our derivative function. dy dx is there anything we can factor? I guess we could factor y out of all three terms on top. So let's do that, simplify it a tiny bit. We'll do y times 2x plus y minus cos of xy all over, and then kind of conversely or similarly, we can factor in x out of each term in the denominator. Let's do that to simplify as much as we can. So we'll do all over x times cos of xy minus x minus 2y. And here is our final answer. That was a nice one. So that's the derivatives portion. On the integrating side, this is going to be a very nice integral to integrate by parts. I'll remind you of your integration by parts equation or theorem. It says that any integral that can be written in the form of u times dv can equivalently be written in the form of u times v, minus the integral of v times du. Let me be very clear here. It looks like a u dv. Okay, so you can see how they just, the u and the v go here, and then the u dv becomes vd, so they flip-flop, okay? So this all comes down to making a good decision in selecting your u and your dv to start things off. In this integral, we have to select something for u and something for dv. Now, afterwards, we're going to have to get those into v and du, so we're going to have to take the derivative of u to get du, and then we're going to have to take the antiderivative of dv to get v, okay? All of these things we need to keep in mind. Now, the best candidate, typically speaking, for u is something that we can differentiate easily, that becomes less complicated to deal with, that dwindles down, let's say, in its complexity. Something like x squared is great for that, because you know you're going to have to take du once you pick your u, and the derivative of x squared is just 2x dx, right? That's simpler than x squared because the exponent has gone down. Now, the choice for dv is typically going to be something that is really easy for us to get the antiderivative of, okay? Something that's really, really straightforward, that doesn't require much work. That's the key, right? So in this case, we're going to pick e to the x dx for obvious reasons. So if dv is e to the x dx, then v, the antiderivative of e to the x dx, as you know, is just e to the x. And that's really great. So what that means is now we can rewrite our original integral into u times v, so that'll be x squared times e to the x minus the integral of v times du. Now, v du is going to be a 2 out front, classic integral rule, right? Times x e to the x dx. Okay, and now we still have another integral to go because we can't evaluate that integral trivially, right? There still needs a bit of work to be done. But what you'll notice is that we've gone down from this integral to this one, which is almost the same, but the exponent has gone down by 1. And so that means we're one step closer to being done here. That's good. So let's keep going, and we're going to have to differentiate by parts again, okay? So let's say step 1, and let's call this one step 2. We're going to use this same formula, integrating by parts. So again, your choice of u is going to be the part of the integrand that's easy to differentiate. For us, that's going to be x. So u is going to be x, and that means that du is just 1 times dx, right? Or just dx for all intents and purposes. And again, dv, the more you practice, the more efficient and the more effective you'll be at making these decisions. But general rule of thumb, your dv is the part of the integrand that is easy to anti-differentiate, right? There's not that many candidates that fit that bill, but e to the x dx is a great candidate to fit that bill. And so we're going to use that one again. dv will be e to the x dx, and that means that its antiderivative, v, is simply e to the x, right? That is good news. So now what we can do is, again, rewrite this integral, right? We're going to rewrite that integral in this way. And so now the original integral, what we're, after all, working to evaluate, is going to be x squared e to the x, this stuff that's already accounted for, minus 2 times this whole thing, right? And so this new integral is going to go uv, so x times e to the x, minus the integral of v du. This time, however, right, v is just e to the x and du is just dx, so that's e to the x dx. And now we've dwindled things down to simply having to evaluate this integral, which I hope you guys know how to do. So now we're down to x squared e to the x minus 2x e to the x. Minus 2 times negative, right? We'll do plus 2 times. And now we simply have to evaluate the integral of e to the x dx, which is simply, as you know, e to the x. And then this is an indefinite integral, so we'll do plus c, plus an integrating constant. And so now let's finish things off with an expression that's as simple as possible. We'll have x squared e to the x minus 2x e to the x plus 2 e to the x plus 2c, right? And we could leave it like this, but you might notice that there's an e to the x shared amongst all 3 of these terms. So we could factor that out for good measure, and we could say that this integral evaluates as e to the x times x squared minus 2x plus 2, and then plus, you could call 2c d for some other new integrating constant that we don't know, or you could just leave it as 2c. Just make sure you have some integrating constant there taken care of. And here is our final answer. And so there you go. Hope you enjoyed it. Hope you tried it on your own, and hope we ended up with the final answer. If you guys have any other recommendations, suggestions for problems in videos to come, please do let me know in the comment section. And thank you so much for watching.